जय हिंद, गुड मॉर्निंग दोस्तों। मेरा नाम सुरेंद्र कुमार है और मैं AKGEC इंजीनियरिंग कॉलेज में असिस्टेंट प्रोफेसर के पद पर CSC डिपार्टमेंट में कार्यरत हूँ। सो today's topic is basically based on Unit 2 for CSC third semester student and who are studying Discrete Mathematics, Digital Computer Electronics, and the topic is from Unit 2 is Boolean Algebra. And in this Boolean Algebra, we are using here K-map for simplification regarding Boolean expressions. So this is my composition of topic. So we will start with the history of K-map and what is Boolean Algebra, applications of K-map, limitations of K-map, and K-map graphical representation, how to represent a K-map using graph or Boolean expression, reducing Boolean expression using K-map. So before starting my topic, it is good to discuss about the scientist who developed this method. So basically this method is developed by Maurice Carnap, who was physicist, mathematician, scientist, and he developed this method in approximately in 1953. It is as a refinement of Edward W. Witt's method, that was Witt chart in 1952 given by him, and it is a discovery of Alan Marquand, who developed this logical diagram in 1881. So Marquand diagram, which focus and now set on its utility for switching circuits. Witt chart are also known as Marquand-Witt diagram or rarely Svoboda chart, and Carnap map as a Carnap-Witt map. So these are different names of the Carnap map and from where this map is developed. So basically approximately in 1952, Carnap published his PhD in physics with the topic of theory of magnetic resonance and lambda type doubling in nitric oxide. After that, he was working in Bell Laboratories. Then he published a paper, the map method of synthesis of combinational logic circuit. So with this paper, he introduced this method of graphical representation of any Boolean expression and simplification of it using this map. So first of all, we will discuss what is Boolean algebra. So basically, Boolean algebra is the category of algebra in which variables are the truth values. It is true or it is false, or you can ordinarily denote it by using true for 1 and false for 0 respectively. It is also called a binary algebra or logical algebra or switching algebra because this algebra used to reduce the expression of for developing any switching circuit. As already I have told you, it is Boolean algebra developed by George Boole in 1854 and it is mainly used to analyze and simplify the digital circuit or digital gates. It is concerned with Unit 2 as already discussed in the topic of Boolean algebra. Now we talk about the applications of K-map. So K-map basically used to reduce the need of extensive calculation by taking advantage of humans' pattern recognition capability. As you know, human is able to understand the graphical things much better than the textual things. So by using this capability, K-map is used. It is also permit the rapid identification and elimination of potential race conditions, that is called don't care conditions. So we can easily collaborate these conditions and reduce the map with the help of, reduce the expression with the help of this map. So in Boolean algebra, let B be one non-empty set with two binary operation and or and a unary operation not. So basically, you know, the binary operations works on applied with the help of Boolean operations. So the two variables are using and or, and a single unary operation is used with the not operation. B contains at least element denoted by 0 and greatest element denoted by 1. So you can represent Boolean algebra as a B comma plus any or and or operation dot any and operation, and this any negation not operation. 0 and 1 are the values to represent these Boolean expression, Boolean truth values. There are some laws of Boolean algebra which are used to solve or simplify the expression: commutative law, distributive law, identity property, and complementary law. So algebraic manipulation of Boolean expression is done basically with the help of these laws. So every element of B is a Boolean expression. A single element is also called a Boolean expression. Every variable name is a Boolean expression again. If A1 and A2 are Boolean expression, then single A1, A1 or A2, A1 and A2 are also called Boolean expression. So you can represent it as a like or 0 or 1, 2 and 3, or you can represent in variable form x1 or x2 and x1 and x3. So these all are Boolean expression, you can represent it. These expressions or operation is basically used for these three types of gates, using these three type of gates. So first is your AND gate. Basically it uses two inputs A and B and provide you one output with ANDing operation. This is OR gate, basically again using two inputs and provide you one output with ORing operation. And this is a NOT gate, which generally negate your input, single input. This is a truth table for OR operation, OR gate, as x equals A plus B, ORing of A plus B. This is its logic diagram of symbol, and it is true for all those values of A and B if any one of them contains 1. So here A is 0 but B is 1, so it is 1. A is 1, B is 0, again it is 1. Both are 1, then again it is 1. It will be false only on when both the values are 0. So here when A and B are 0, so it will be produce a result of 0. And AND gate basically works on when both the values are true, then only it will be true, otherwise it will be false. So A and B is false, then it is false. A false, B true, again it is false, because what should be true? A is 1, B is 0, then again it is 0. That means true, false equals false. And NOT gate will generally negate its input into output. Right? If it is giving 0, it will give 1. If input is given 1, it will output will consider as 0. Simplification of Boolean expression is our topic here. So an implementation of Boolean function requires the use of logic gates. So a smaller number of gates, with each gate other than inverter having less number of inputs, that may reduce the cost of the implementation. So our basic purpose is to studying this K-map and discussing this K-map to basically reducing the cost of the implementation, and this cost of the implementation will be reduced with the help of simplification of Boolean expression or reducing the expression. So there are two methods for simplification of Boolean function. So the two methods are algebraic method by using identities, and the second one is graphical methods by using Karnaugh map. So K-map is mathematically easy and straightforward because it is a graphical representation, and as I already have discussed that graphical representation is easy to understand for human cognition. A K-map for a function of n variable will consist exactly 2 raised to power n cells. So this map works with cells. So you will create cells like this for one variable, 2 cells, 2 raised to power 1, 2 cells, variable 1, for 2 variable, 2 raised to power 2, it will contain 4 cells, for 3 variable, 2 raised to power 3, it will contain 8 cells, for 4 variable, 2 raised to power 4, it will contain 16 cells, for 5 variable, it will contain 2 raised to power 5, that means 32 cells, and so on. Some terms which is useful before discussing the K-map is literal mean terms of n variable. Literal means a variable or its complete complement is called a literal. For example, A, this is a literal, or A dash, that means A negation of A is called your literal. So any variable A and A dash, B and B dash are called literal. Min terms of n variable. So it is a product of n literals. So for example, if you have 3 variable x, y, z in any function f, so there are 3 literals, and these 3 literals basically appears exactly once in that min term. It will be either true or it is complemented form, but not both. In a single min term, for example, x, y, z, this is a min term. This is a min term, x, y, z, and this min term contains x, y, z, but it will not contain as x, y, z. So x will not be there 2 times. X can be x, y, z, but not both. X bar will not be there in a single min term. So only maximum 3 min terms. If we have n literals, so in a min term there will be maximum n literals in a single min term, or less than n. Or the equivalent value of this min term is 1. So every min term will contain, or a value of every min term will be exactly 1. Max term, as min term is basically comes with sum of product. It is basically sum of product. Yep, only you can say it is product. Sum of product comes in sum of product, or it can say product of variables. If we talk about max term, so it is basically, it comes in POS, product of sum, and it is sums, yani A plus B plus C. This is one minterm, max term. This is one max term. And same as in minterm, you know, okay, every max term contains exactly once a particular literal. So now we talk about the adjacent minterm and maxterm. That means A bar B C and A B C. Here the single change in A, B and C are same, but A is different. So adjacent minterm or maxterm are those minterm or maxterm which change by a single literal or single variable. So the single variable changes, A bar is changed with A. So this is your adjacent minterms, or it can be solved with the help of BC with the identity property A plus A is equal to BC dot, this is 1 equals BC. So using this property, you will solve the K-map. So adjacent minterms, as we are taking here 4 variable K-map. So adjacent for 0th cell is R1, 4, 8 and 2. These are the adjacent cells for this particular 0th cell. You can see okay, the changes is here single change, again here single change in C, here the single change in A, right, here single change in B. So single change or minimum change, you can say, are called adjacent minterm. Now we start with the representation of K-map. So as already we have discussed about, okay, if we have a function having f with one variable, f with two variable, f with three variable, f with four variable. So we have a map with 2 raised to the power n number of cells. So for one variable there are 2 cells. That means this is your K-map for a single variable. For 2 variable we have 2 raised to the power 2, 4 cells, this one and so on. So we start with 2 variable K-map. So 2 variable K-map, first of all, the thing is that how we can represent a 2 variable K-map. So in 2 variable K-map we have 4 cells, and these cells are represented with the help of this diagram. So A and B are 2 variables here. We can denote these variables value B 0 and 1, same A 0 and 1, or you can represent it as a horizontal manner like this, A B 0 0 0 1 1 1 1 0. As already I have discussed that K-map uses adjacent minterms or maxterm. So adjacent minterm or maxterm basically used from the concept of gray code. Gray code basically comes from the soft encoding. Soft encoding, it is one time this direction and again next time in opposite direction. So every time it changes its direction. So in the same way, every time only one variable changes its position, 1 to 0, 0 to 1. So now here we can use this representation. For 0 is 0th cell, numbering of the cell is important. So 0th cell, first cell, second cell and third cell. For 3 variable K map, we have this kind of representation, or you can have vertical also in this way. A, B, C, 0, 0, 0, 1. Sorry, something. It is basically you can write it as a, this is A, this is B, C, or again you can write it as A, B, C. So in any way you can write it. So I am using this one of notation. So you can write it 0, 1. It is 0, 0, 0, 1, 1, 1, 1, 0. Right? So we are removing this for clarification. So this is your 0 cell, 0, first cell. This is your second, third. So this is your fourth, fifth. This is your, sorry, 0, 0, 0, 0, 1, 0, 0, 1, 1. This one is your, this is your third cell. So you can denote it with the help of these numbers. 0, 1, 1. This is your third cell. This is your second cell. This is 1, 0, 1, 1, 0. This is your sixth cell. Because your fifth cell will be, this is fourth, this is fifth, this is sixth, or this is 7. So in any way you can represent it. So the simplest way is representing this way. So we'll use this kind of map here. So 0, 1, 2, 3, 4, 5, 6, 7. Same 4 variable map, you will have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So in this way, you can easily draw the graph. Now, a second way of giving your K map with the use of min terms M0, M1, M2, M3, M4, M5, M6, M7, M8, M9, M10, M12, M12, M13, M14, M15. So because the expression is given or function is given in different ways, it is in the form of expression, it is in the form of function, like f equals summation of M0, M3, M5, or you can give the function like x bar y plus y z, right? Or you will be given function like f equals 1, 3, 5. So in many ways the function is given and you are asked to solve these functions. Now we start with 5 variable K map. So again you have a 5 variable K map here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, then 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. That means you can join 2 4 variable K maps here. So same 6 variable K map. Now we start with the solution of these map with different combinations. For example, you have a 2 variable K map and you are given value 1, 1 in this way. So you can easily combine it with the help of pairing. So these expressions will be written as, here you will see what variable is not changing. You will write those variables. So here A is changing from 0 to 1, but B is not changing. So the expression for this is B bar, because it is 0. B complement dependent as 0. If you have 1 here also, you will combine with these two ones, because you have to maximize the pairing. You will create pair, you can create quad, you can create octet, you can create hexa values. So here you can write it as a B is changing 0 to 1, so the expression will be A bar here. So for this it is B bar. If you have all the 4s here, so you will combine these 4 and the expression will be 1, because B is changing and A is changing. So as you know, the minterm is represented, the value of minterm is 1 always. So it will be 1. If you have single 1 here, then for example you have this one only, so there is no other element or minterm to pair. So this will be written as A bar B, because value of B is 1. So in the same way you can write this one also, because cross cells will not be combined, only adjacent cell will be combined. So this will be written as, here A is 1, that means A, and B is 0, that means B bar. So in this way you can write the expression and solve the K map. Now we come for the 3 variable K map. For example, you have 1 here, 1 here, same, you will combine this and the expression will be written as A, because A is changing, so A will not be there, there will be B, there will be B 0, this will be B bar, and C 0, that is C bar. The expression will be B bar C bar. If you have 1 here, so you will not create a single element here. You can use with the help of overlapping method. Like you can use, sorry, not overlapping, it is folding method. It is folding. You can fold this map and combine these two ones, and the expression will be written as, you will see 0, B is changing 0 to 1, but C is not changing, that means C will be written C bar. A is not changing, that is A bar. So expression will be A bar C bar. If you have 4 ones here, like, then you can combine it in this way. You will combine all 4s, and the expression will be, A will not be written here because A is changing 0 to 1, but you can see here C is not changing. So expression will be for these 4 quad is C bar. So thank you very much. We will discuss further 4 variable map in next lecture. Thank you very much.